Now I hope you guys really enjoyed that wonderful cold start I gave you of my PS4. It's been hibernating in my closet for over a year now. Today I'm going to use Fusion 360 and Generative Design to make a really cool part, but a functional part to hang my PS4 up on the wall since I'm getting back into story games again. Because after I found out I was trash at OG Fortnite. Alright, I hope you guys really enjoyed that. Now let's dive in. Now when it comes to creating a part that depends on the features of another part, you're going to start by taking some measurement. That's going to be the most important part. So I highly recommend you guys take your time on this part, because if something fails, you're going to have to reprint stuff and you'll have to account for tolerances. So here's where I want my PS4 to be held on the wall, the slit over here. And we're going to start by taking the measurements of that with my calipers. Make sure you get a decently loose enough fit, not something that's like rock hard, but something that can slide in and out. So we got about 23.25. The next thing you want to do is write down all of that in a book. Now I have written down all mine on my book already. Here's what I got. I got the 3 features of the PS4. So the upper area, the lower area, and the slot. Then you kind of plan out your features and how you want to do it. For generative design, here's how I did it. We're going to create a preserved geometry here with our essential dimensions. And then we're going to create a filler geometry, which the generative design algorithm will then edit out to turn into the rib we want to make. Alright, so now we're in Fusion 360. What I've went ahead and done here is created our backplate, and that contains our mounting holes and the rail, which contains all our essential measurements. So now basically I've created a functional component, but now we have this big block here, and I'll explain more about this later once we get to the generative design tab. But for now, I want you to think the point of generative design is that you go ahead and create the component in its bare bones with just the effective dimensions and the functionality of the part. And once that's done, we can go into generative design. Now you have 2 options here. You have the fluid path or the structural component, and we're going to be working with structural today. If you've never been here, these new icons might be overwhelming, but Fusion's made it really easy by helping you work from left to right. So you guys can learn more about this tab over here or better YouTube tutorials. But here's a quick overview on what I did. We're going to start with preserved geometry. Preserved geometry essentially means geometry that has to be preserved.
Yeah, no shit, Sherlock.
For example, so here's our essential geometry that is necessary for the part to function, which is this rail and the back plate. So these 2 will not be modified during the design. Obstacle geometry, actually we don't have any obstacle geometry in this design, but you can go ahead and read about it and use it in your design if you have obstacles that you don't want Fusion to touch. But what I do want is the starting shape. Now the starting shape, what that's going to do is click remove material. Let me go back to drawing. So we give Fusion a starting shape, and Fusion can modify that starting shape based on the load case that is given. So over here, you'll see once we define our load case, Fusion's going to take that yellow box that we have and shrink it and modify it into the best organic shape that can support the load that's going to be sitting on our bracket. This is going to save you a lot of time where you'd have to make this design manually, print it, put your PS4 on it, have it fall down on your head, and then go make another one that's maybe a bit stronger, or you overbuild it and you waste material on a component. So We're going to go, our next part is structural constraints. This is going to define where the object is fixed. So this wall bracket is where our object will be fixed, and from here the load cases are going to be acting downwards. So we're going to define our structural loads, and it's a Newton force. You can convert it if you want, but I prefer to use Newton force. And the way you calculate this is, I have it right up here. You could search up the weight of your object or measure it yourself. Mine is 2.8 kilograms. Then you plug it into ChatGPT, because other Newton calculators might not be using Earth gravity, so you might get funky numbers. I recommend just using ChatGPT, where you can define what you want, and it spits out this number. And that's about almost done. Next is design criteria. Now this is also important. This defines how you're going to be manufacturing your components, so Fusion can better optimize the way your part is made, so it's easier to manufacture with that method. Now we're not going to be using CNC milling or any of these, but additive is 3D printing. That's what I'll be doing. And we'll be printing Y up. So that's our orientation, and that's correct. And one more, study materials is also important. I'm going to go to my favorites where I have PLA. Okay, now that we have our study materials defined, we can go ahead and click generate. And also, I highly recommend you check the pre-check tab. This will give you all the warnings that you need to address in case your design is not ready for generate. So once we have a green check mark, we're ready to go. And we can send this off to Fusion's servers. Now these crappy servers are going to take forever while your very powerful and capable computer sits idle. And we'll be back once it's done. And Fusion spits out 2 design options for you. Now, if you really don't want to go off the looks and actually want to go off logic and which to pick that is the safest component, you could use this little chart right here. So when you click on a certain component, which is this one right now, you get up all these stats. And if you're not a structural engineer, you might not know most of these, but mainly you want to be looking at the safety factor number. Now, on average, to give you a perspective, engineers for structural loads such as buildings, I believe they aim for a safety factor of 2 to 3. So 184 is definitely way overbuilt and crazy. And we look at design 2 right here, it gets a safety factor of 94. So technically both of these designs can hold it, but this one obviously looks cooler, but when you think about 3D printing, this one also looks more messier to 3D print, and there seems to be some problems with the bottom plate here. So we're going to definitely pick this one and finalize it. So once this is done, you can design from outcome. When you click this, this will take you into this tab with your design all done. Now this is a very much modified version of my design. When I got my design, it was like that. So this was my design. I added 3 extra holes, and then I realized it would be too crooked if I just screwed the whole thing on the top and had no support on the bottom. So I went through some more designing after that, and I took away some material, added 2 holes. Now this is my final design. And when you make drastic changes like this to your component after a generative design process, it's my mistake. I should have made this before. But if you do end up making it after, there's no problem. You could go to the simulation tab, and it's almost like generative design, but you could run a simulation test. I'll show you guys right now real quick. We're going to generate a new simulation study. We're going to click static stress because that's what we want. Now we have our thing. It's the same thing. We're going to work from left to right. So we're going to go to our materials, and our design material is already PLA. Then we're going to define our constraints, which is our back plate. And then our loads, which was 27.44. And that should be about it. This tab is much easier than Generative Design tab. So once we check everything's ready, we can do another solve and sit back and watch a whole Netflix TV show while this is over. Okay, so once we're back with our design, your thing is mostly going to look like this with the safety factor chart. And as you can see, this is how a safety factor scale looks like. So the 2 to 3 is where most of your design should be at always if you want a decently built design. But we have exceeded the safety factor of 15, so this design is basically unbreakable when it comes to our load case that we have defined. And to better observe this, we're going to switch to the stress tab. Now this should explain everything way better. This will teach you how to identify weak points in your design and where you need to maybe change some stuff, add some fillets or chamfers, spread the load, and maybe thicken it up on that specific area. Now your deformation scale, it's most likely going to be adjusted, and this is really not how your part will actually look like when there's a load applied. The adjusted is to help you visualize it better. Now you go all the way up to 5x to make it look crazy, but in actual, when you click actual, the deformation is so like unnoticeable, you can't really tell. But I don't know if you guys noticed it, but yeah, you can't really tell. So you use adjusted to help you visualize it better. And we can also animate that to, there we go. Now when we animate this, it's super useful to see where areas of stress grow as a load is placed on the subject. So I identified this seam over here gets a lot of stress when the object is placed on it. And it's actually like not even crazy. You shouldn't even be worried about it if it's in the yellow range, so there's no problem really. But I did want to experiment with it, so I went ahead and added a chamfer or a fillet, and turns out it actually made it worse. So our maximum pressure at this point became 40 from 30, I believe. Let me go back to this design. So yeah, our maximum pressure here was 30 psi, and after the fillet it was 40. So it was doing better with the original design, so I left it and I confirmed everything's good and it's ready to go. I don't need to run any more generative design simulations to redo this bottom area, but yeah, everything's ready to go. So we click finish results and we can go ahead and 3D print this. Now we're here in Bamboo Studio. Click auto orient and it's going to pick the best way to 3D print this. So this is our Y-up orientation that we had defined in the simulation. Now the rest of the stuff we'll need is we're going to definitely need supports for these. So I'm going to put it to tree, auto, and I found tree organic uses the least amount of filament. Speed, I generally like to turn this down for 50 on the initial layer and everything else I leave as default. One skirt loop to get the filament flowing properly. And one more thing in strength, that you want to use a gyroid infill. Now the gyroid is the best type of infill to provide strength in all directions. I'm going to go ahead and slice. Inspect the model, make sure everything's correct. So now we have our skirt loop, our supports, and our design is going to print perfectly. Now when you have organic shapes like these, you really want to print them Z up. It's going to make it way easier for your print and it's going to look nicer. If you print them with supports or any other way, it's going to look jagged and just very bad. Yeah, with all that done, we can click print plate and send it off to our printer.